Welcome back to Sustainability Ventures, Earth. For decades, scientists have warned about many climate risks. But here's something most people don't realize. Ice age prediction models have repeatedly failed. At different points in history, models predicted imminent global cooling, advancing glaciers, and a new ice age within centuries. Yet instead of ice sheets moving south, we've seen warming dominate global trends. So what went wrong? Today, we're going to unpack why ice age models exist in the first place, what they get right and what they miss, and why long-term climate prediction is far harder than headlines suggest. This isn't anti-science, it's science examined honestly. Let's slow down and look at why ice age predictions keep missing the mark. Snow. To understand ice age predictions, we need to start with why they exist. Ice ages are not random. They're linked to long-term orbital changes known as Milankovitch cycles. These include changes in Earth's orbit shape, variations in axial tilt, and wobble in Earth's rotation. Together, they alter how sunlight reaches Earth over tens of thousands of years. Historically, these cycles align with past ice ages. Glacial advances roughly match orbital timing. So the logic seemed simple. If orbital conditions are trending toward cooling, the onset of another ice age. However, Earth's climate system isn't driven by orbit alone. Early ice age models relied heavily on orbital forcing, but here's the flaw. Climate is not a single input system. Real climate behavior depends on atmospheric CO2 levels, ocean heat storage, ice albedo feedbacks, volcanic activity, cloud dynamics, and biosphere responses. When early models focused too narrowly on orbital cooling, they underestimated other forces that counteract ice growth. In other words, the math was elegant, the system was incomplete. Ice age predictions weren't wrong, they were underspecified. One variable completely reshaped ice age expectations: atmospheric CO2. Past ice ages occurred when CO2 levels were far lower than today. But modern Earth has something unprecedented: massive fossil carbon release, rapid atmospheric accumulation, and human-driven forcing, not orbital. Even if orbital cycles favor cooling, high CO2 levels can overwhelm that signal. Many early ice age predictions failed because they assumed CO2 would remain relatively stable. That assumption no longer holds. The climate system is now operating under conditions with no direct historical analog. If there's one component ice age models consistently struggle with, it's the oceans. Oceans store over 90% of excess heat, redistribute energy globally, and delay surface cooling for centuries. Ice sheet growth requires sustained cooling, not just temporary dips. But oceans act like thermal flywheels. They slow, buffer, and delay climate transitions. Many ice age models assume cooling will express quickly at the surface. In reality, ocean heat inertia resists glaciation far longer than expected. This alone can postpone ice age conditions by thousands of years. Ice doesn't just respond to climate, it actively changes climate. Ice sheets influence atmospheric circulation, ocean currents, and albedo feedback. But ice growth is slow. It requires persistent cooling, stable snowfall accumulation, and limited summer melt. Many models assume ice sheets respond smoothly, In reality, they surge, collapse, fragment, and reorganize unpredictably. That makes precise ice age timing incredibly difficult to model. Ice age prediction models don't fail because science is broken. They fail because climate systems are deeply nonlinear, long-term prediction magnifies uncertainty, and Earth doesn't behave like a clean equation. True scientific literacy means accepting limits, not pretending certainty exists where it doesn't. Did this change how you think about climate predictions? Let me know in the comments. If you value clarity over sensationalism, like, subscribe, and share this video, because understanding climate requires humility, not hype. See you in the next episode.